Okay, well, that's too bad. Okay, well, here we go. Okay, so Q, sorry, forgot to record. Sorry, anyone that's watching. Okay, but we're doing this. So, yes. So this is our Q area. So we go all the way to the top, halfway down. That's where we're at. 110.625 millimeters minus 90 over 2. That's y bar times the area is what? 90 times 40. All right, what do we get? We get 236,250 millimeters cubed. Okay, so then we have little q we can solve for because we know v and I. So little q equals 7 kilonewtons times 236,250 millimeters cubed all over I. 144,472,500 millimeters to the fourth. And we get little q equals 11.45. I guess I changed this to newtons per millimeter. So, okay, so this is the shear flow that is transmitted by just one of these surfaces. So not both, only one. Okay, so that's important to remember. And the folks at home didn't get to learn that fun lesson, so I'm gonna write it down. All right, so this is the shear flow that must be transmitted by one surface of the bolt cross section. Okay, so then we're supposed to find what? Oh yeah, the shear stress of the fastener. So you can do that two different ways, right? There's usually more than one way. So now we're back at this equation. Q is less than or equal to NF VF over S. How do we get shear stress into that equation of the fastener? Shear stress of the fastener?
Oh, there we go. That's fine.
Yeah, right. So VF equals the shear stress of the fastener times the area of the fastener. Remember that old gem? All right. So the area of the bolt equals pi over 4 times 8 millimeters squared. So that's 50.27 millimeters squared. Cool. And then, oh, that was nice of you to say that. So then this equals Q is less than or equal to NF tau F AF over S. So So you rearrange that, and shear stress in the fastener is going to be greater than or equal to QS over NFAF. What's NF? Yeah, I mean, but like, yeah, good job. Yeah, very good, yes. One, good job. Okay, so we have Q was 11.45 newtons per millimeter, and the spacing was 200 millimeters. That was given. All divided by 1 times, we're going to call this bolt surface, times the area fastener is 50.27 millimeters squared. So we get 45.5 megapascals. Sweet, not too bad. So shear flow, the thing that's being held on to the other thing. Make it as simple as possible. Sound good? Q is the thing that's being held on, that area. Y is the distance centroid to centroid of that area. Okay, then what I've become fond of doing on these problems is asking what is the maximum shear stress in this same situation. So then what do you do? What equation do you use for that?
The other one?
The other one. Good job. So you would have your equation sheet. It's a good answer, Gavin. The other one. So we really only have 3 equations for this quiz, right? We have little q equals that, little q is less than that, and the other one being shear stress equals VQ over IT. Which is very similar to this one without the T. So 3 equations. I think that's all you have to know tomorrow. But it's unique. Like this problem, we've now done a homework problem using this picture that was different than this. We're doing this problem that was different than our homework problem. And I posted an example online. No, it's different. But there's like 3 versions. The example online is different. Yes.
So like for that one,
Yeah.
if we're doing the max,
Yes.
what would T be?
What would T be? So where does the max happen? Centroid, right?
Would it just be the middle beam then, or?
Yeah, so it would be like if this, they always draw that cool little like bullseye for the centroid. If this is the centroid, then your Q, what area would you use for Q? 40 times what? 300? No.
Would be the
That's
area of
cool.
the whole entire system?
No. So remember it's from, so the area is, yeah, where you're taking the shear stress to above or below. Yeah, it'd be way easier to go to the bottom, right? So we go where we're taking the shear stress. So right now we're taking the shear stress here, and we can do everything above, which would be annoying, or we could do everything below, which isn't very annoying, right? Cool. All right. So I think going back and forth trips you guys up a little bit. It seems like yeah. All right. Good question, Nate. Good job. Okay. So we know T equals 40. We know this is the area we're going to use, and that's at the centroid. So this is how tall it is. So what's Y bar going to be? Yeah. The center, the y bar is going to be like wherever the middle of this is, centroid to centroid, right? So it's just going to be 189.375 over 2. Oh, I like made a whole nother picture to do this. All right. So here we go. Look at me being prepared and then just making a mess out of everything. It's kind of how I roll. 9.375 millimeters. This is our neutral axis. So that's the max. This is our area. All right, so shear stress equals V times big Q over I. Is I just of one part of this? The whole thing. It's always the whole thing. Stays the same. So I stays the same. V stays the same unless it's like a V that changes along the length of the beam. All right, and Q, this is going to be the area for Q. So we've talked about that. So Q equals the area. I'm going to do it the same way I always do. Y bar equals 189.375 divided by 2 millimeters. Then we have 189.375 millimeters times 40 millimeters. I had Q top before. I was way dumber. That was way more work. But it'd be the same answer, right? Whether you go Q top or Q bottom. So Q equals 717. 258 millimeters cubed. Okay, just for fun. No, you don't even want to think about Q top? Yeah. I mean, or like for your betterment, but we're not, yeah, I guess it's maybe a better way of saying this. Yes, Aiden?
Is there beam deflection on this quiz that we're taking?
No,
Oh, okay.
yeah. No, yeah, no. That's next. Well, it'll end up being on the final. Yeah. No, just shear stress and shear flow. Cool? Yeah. Yeah. We didn't, I'm not, no. No, we're not doing that yet. You haven't even done homework about it yet. Oh, yeah, you don't have to do any integrals. Yeah. Yeah, there's no integrals. Okay, okay. Alright. Okay. So, there's Q. So, that's a big thing, is that this Q is different than this Q, right? Different. So, make sure you change those. Okay. So then we plug things in. Shear stress equals V, 7,000 newtons, times Q, 717,258 millimeters cubed, all divided by I, 144,472,500 millimeters to the fourth, times T. T equals 40.
So we have to use that 35 kilonewton meters that you gave us earlier?
No, cause well, if we had solved for the bending stress, we would, but I'm not gonna do that.
Even though the ass was the next bending stress?
I said I'm not doing that.
Not gonna work.
Yeah, yeah, said that. Where would the maximum bending stress be? Ugh.
Centroid. At the top, I don't even know. We don't have to do that.
Bending stress is opposite. Bending stress is opposite.
At the top.
Now I'm changing the quiz. I printed 62 of them and I'm changing it. All right. Bending stress, 0 at the neutral axis. Shear stress, maximum at the neutral axis. Bending stress, maximum at the top or the bottom. Shear stress, 0, top or the bottom. Sound good?
Got it.
Got it. All right, good. Because you just wasted 62 pieces of paper. Alright. Okay. I'm just kidding. Calm down. Okay. Alright, so final answer. Tau equals 0.869 megapascals. So that's how much shear stress the whole thing can handle, right? And this is the shear stress in one fastener. They're very different. And it makes sense that a fastener is way stronger than a wood board, right? It tracks. Okay. All right, how are we feeling? Better? Okay, good. How are we feeling about this problem? Do we just want to do like part A? Do we want to do none of it? Okay, we'll vote. The options are part of it, none of it, and I will not do all of it, but like we could see where we're at. So raise your hand for part of it. Okay, that's pretty high. We're doing part of it. Okay. Do you guys have
You
a?
get that option on the exam too, or?
I mean, you always get that option, Vinny. Like, that is always an option to do part of it, none of it, or all of it. But yeah, that's totally up to you. You know, it makes it easier for me to grade if you either ace it or you just like don't do it. You know, those are my two favorite options. But yeah, okay. All right, we're not gonna do part D. How about that? I'll give you that. So maybe we should do either part A or part B since we just did the maximum. Where would the maximum happen? In the middle. What would your area be? What would the Y bar be for this one?
Half of.
Yeah.
Yeah.
Half of what we're given? Yeah, so 100. It would be, if this is 200 tall, then it would be 100. Okay. And the area would be 200 times 150. This isn't, okay. So we got that taken care of. Okay, so let's do this. This one though, let's see what we know. We have this equals 6 meters. So there's 2 meters here, and there's 4 meters here. And it carries 36 kilonewton load. Oh, look at that, that's written there. The cross-sectional dimensions are written there too. Section AA is 0.8 meters from beam B. We're supposed to determine the magnitude of the shear stress in the beam at point H. So what equation is that? Is it little q or is it tau? Tau. This is, shear stress is tau equals V times Q over I times T. Okay, so what are we missing in this equation? Huh? Q, but we know how to calculate that, right? What else are we missing? B, right? And I. So we NT. We're missing the whole thing. We don't have anything. Alright. We're missing it all. So we have to calculate all of it. How do I find V? A shear diagram. Good job.
Are you gonna make us do that on the exam?
Maybe. I'm not making any more moment diagrams. Done with those. Some of you get artistic. I'm just kidding. Yeah. Okay, so we have to draw a shear diagram to find V. Okay. Alright, and we're gonna draw a line here. We're not gonna do part D, so we don't have to draw a moment diagram. Just a shear diagram. Shear diagrams aren't bad, especially with point loads. So, oh boy, there's reactions. Let me just tell you that the reaction at A is 24 kilonewtons, and the reaction at C is 12 kilonewtons. Cool. All right. So, shear diagram. How does it start? Goes up. Goes up to 24. Nice. Then it does nothing, right? To here. It goes down by 36. And then it does nothing. Oh, I messed this up. It doesn't go down to 36, it goes down by 36, right? So we're at negative 12. And then it does nothing until it bounces back up to 0. Okay, so reading the problem one more time. At section AA, determine the shear stress in the beam at point K. So what is V? Sure it's not 12? 12's on the table. It's not 12. So it's where you're calculating it. What if it was the maximum shear stress in the beam? What would you pick? Still 24. Good job. Okay. And I don't know, the only way you'd pick 12 is if they picked a point over here. Cool? So we know V equals 24 kilonewtons. So we know our first thing. Then we have to know Q for H. So I draw a line through this. What is Y bar? Yeah. 200 minus 90 divided by 2. So Q, we go all the way from the centroid to the top. That's 200. And Y bar of this area is the middle of it to the centroid. Centroid to centroid. So, Q equals 200 minus 90 divided by 2. What's the area? 90 times 150. That's my bad writing. Okay. So, we get Q equals a giant number. Millimeters are annoying. The numbers are so big. 2092500 millimeters cubed. That means I is going to be huge. Okay. T. What's T? 150. Right? It's actually 150. I think you can't read my right, or do you?
I said
know?
150.
Oh, okay,
That's it.
that's good.
I said 50
Okay.
first time.
Oh, okay, then you know. Okay, so T, 150. Is there ever going to be a different T for this problem? No. 150 millimeters. Okay, we got V, we got T, we need I. BH cubed over 12. Base, 150. H is 400 cubed divided by 12. And that equals 800 times 10 to the 6 millimeters to the 4th. We just plug that in. Okay. Shear stress at H equals 24 kilonewtons times 1,000 newtons per kilonewton times the giant Q of 2092500 millimeters cubed, all divided by I 800 times 10 to the 6 millimeters to the 4th times 150 millimeters is the thickness, and we get 0.4185 megapascals. Sweet. Okay. If we look at this picture, is the shear stress at K going to be greater than or less than the shear stress at H?
Greater than.
I like your confidence, but less than it is. Yeah, so this is only 30 millimeters away from the bottom where it's 0, right? So it's, and then this one is 90. So this one's closer to the centroid, right? And the centroid's where it's a maximum. Good? Feeling super great? Not super great? Feeling slightly better?
Yes.
Okay, that's all I can do. It's a win for me, is slightly better. All right, but there's answers for everything I didn't do. Feel free, I know you guys have nothing else going on in your life, so just go do some more of this. Sound good? Huh?
For, yeah, because it says
Oh, that's the final.
add section AA.
That's section
Determine
A.
magnitude.
Yeah, that's how we
Still
pick.
use the same one.
Huh?
Like for part B, your B would still use.
Sure would.
So I think you said it already, so it was like, I guess where your red mark is.
Yeah.
It would be 12.
You got
Would it
it.
be negative 12 or?
It doesn't really matter because we always do magnitude, because remember we like determine shear based on inspection.
Just mark wrong.
No, you can do whatever you want, but yeah, it's usually a magnitude. No problem, good to see you. Matt, how you doing? You're gonna make it through this week?
Have like a third amount of time to study.
You'll be fine. You get it. There'll be numbers. I'll give you numbers.
Yeah, but he didn't teach us in numbers for half of it.
That means you probably learned it better.
No, I was lost until I was
Getting better.
This is, that was helpful.
You feel good?
Yeah, that was helpful.
Good. Okay, good.